Hey folks, this is Captain Jones here to talk to you about operating system routines. So we're going to look really closely now at how the trap instruction allows us to make system calls, how to run these operating system routines that allow us to interact with the hardware. We're also going to introduce to you a new instruction called RTI, which stands for return from interrupt, or which we'll use. It's effectively the same as returning from these operating system routines. Along the way, we're going to describe something called the trap vector table and in the process of these operating system service routines. And then also, hopefully by the end of this lesson or by the end of reading the chapter in the textbook, you can trace operating system service routines that are sort of provided to you that allow you, the programs you write to be able to receive characters from the keyboard, transmit characters to a display, halt the processor, and even transmit a full message or string to a display. So let's get started. Okay, so I'm going to start here. This is our earlier lesson on operating systems. Recall that the way we interacted with hardware is through these trap instructions that sort of, made a request of the processor to do something with hardware. So ideally, when that instruction, let's say this is a user program and we make a call to a trap instruction, we want something to happen in the hardware, so stuff is going to happen, and then we need to be able to return to the very next instruction, having completed that stuff in hardware with the user program, not having any other sort of change to the processor state. So there's a very specific sequence of events that needs to happen in order for this trap instruction to execute. So this is the format for the trap instruction. The opcode is 1111. And the lower 8 bits of this trap instruction are an 8-bit vector that we'll look at in a second that sort of specifies which trap program or which operating system service routine we want executed. So this is a big picture of the memory map. There's a lot going on, but I'll walk you through it a little bit at a time. I want to draw your attention down here to kind of this lower portion, the user space, and we're going to zoom in here. We're going to imagine that we are we're tracing some user program, and at some point that user program makes a call to trap 21, which is the service routine that takes a character in R0 and puts that on the display. So in order to execute this trap instruction, we need to ultimately move to system space where that code is that it can access the hardware page, and then come back. And so there's kind of I've got here 3 steps in order to be able to do that. Number one, we're moving from system space to user space. So the first thing we do is we save the user stack pointer into a special register in the LC3 processor. And in its place in R6, our stack pointer, we will load the system stack pointer. So now the stack that we're using is our supervisor stack. Onto that supervisor stack, we are going to push the whole value of the processor status register, which you might recall has information about our priority level and our condition codes. And we are going to push the current value of the program counter. The program counter is incremented right at the start of getting this instruction, this trap instruction. So the program counter points to the very next instruction that's supposed to execute. Both these values get pushed onto the supervisor stack, and then we clear the privilege level in the actual processor status register. So this is what converts us from sort of user mode to privilege mode or to supervisor mode. Next, we need to figure out which code that we want is executing. So what the processor does is it takes the vector that's down here, it looks at that location in the memory map. Okay, so you can see here I'm calling trap 21. So then memory location 21 has the address of the starting instruction of my service routine. 0306 is the very first instruction in my memory that performs some service for me. In this case, it's putting a character out to the display. So at 0306, there's some code that puts that character on the display. When that code is finished, instead of using the return instruction, it uses this instruction called RTI, which is a very simple instruction. The opcode is just 1000, and we don't use any of the other fields. RTI is a very important instruction, though, because it basically performs this first step of moving from user space to system space, but in reverse. So when the processor sees RTI, what it's going to do is pop the program counter off of the supervisor stack and into the actual program counter. Then it's going to pop the next value off the stack into the processor status register. And so effectively what we have done here is restored the state of the processor to where it was right as we were executing this trap instruction. And then lastly, it's going to switch those stack pointers around. So it's going to save the system stack pointer to a special register in the LC3. It's going to reload R6, our stack pointer, with the saved value of the user stack pointer. And then it's going to start the instruction cycle back at the top. And at this point, the program counter is pointing to this next instruction. So we're back in user space. We're back to where we were before. And we've effectively completed this service routine. We can also execute service routines from inside system space. And this process is actually a little bit easier since we're already in system space. We don't necessarily need to do this business of sort of switching from user to mode to privilege mode or back again. So you can see here I've got effectively the same process, but the steps are much simplified. You can imagine in this case here, I'm in maybe the same trap instruction that was going to display character, and there's another call to a different trap instruction, trap 27. This is just a random one. So the same thing's going to do. The same thing's going to happen first. I need to sort of save the state of my processor. So what I'm going to do is push the value of the program status register, processor status register, and push the value of the program counter onto the supervisor stack. I'm already in system space, so R6 already has the value of the supervisor stack pointer, so I don't need to do any funny business with that. I can just push those straight to the stack. This trap instruction, just like the one we looked at before, 27 points to the spot in memory that has the value of the first instruction of that service routine. So in this hypothetical example, 05A0 is the very first instruction of this trap routine, or this service routine that I want to have executed. So step number 2 is going to be to get that value and jump to that location. Here in memory location 05A0 is some other service routine that I want to occur. And at the end of that service routine is the RTI instruction. So the RTI instruction just sort of needs to revert, our processor back to where it was before. Since I'm finishing still in system space, all I need to do here in step 3 is pop the first value off the supervisor stack and put it into the program counter, and then pop the next value off the stack and place it into the processor status register. And that effectively reverses this first step and restores my processor to whatever state it had immediately, as it was executing this instruction. And then this service routine at 0306 can continue executing with this trap instruction having completed. So then the last thing I want to bring to your attention are that there are a handful of trap instructions that we've already kind of seen in the book, and there are 1 or 2 more I think that have yet to be introduced. But this is just a short list of what those trap routines are, and the textbook discusses a few of them. Let's see if I can pull this up. So you've got in section 9.3.6 routines for handling I/O. So we've got a trap routine that handles input, getting a character from the keyboard. Another trap routine that can output a character. You've got a trap routine that performs halting of the processor, and there should be one more, a slightly updated version of the input routine that allows for some code reuse. And then the last one is this one called put S, which is short for put string. So instead of just placing a single character onto the display, this trap routine assumes that R0 has the starting address of a null terminated string home message. that whole message will get placed on the display. So at this point, what I would do is encourage you to sort of spend some time with these programs so that you understand how they work. And there's some excellent examples of how to use our output devices, the keyboard status register, the keyboard data register, the display service status register, the display data register, and then maybe, if you're feeling a little bit like there's a lot going on, maybe review some of this material. So today what we talked about is how is it exactly that our system is able to execute this trap instruction to access hardware, which was complicated slightly by the fact that it's not just like a normal subroutine call, since we have this privileged and unprivileged modes that we need to worry about. So when we execute the trap instruction, we need to, if we're starting in user space, we need to do some steps that save the state of the processor and effectively move us into privileged space that get reversed when the end of that service routine issues the RTI instruction. The way that traps work, or service routines work in the LC3, are that memory locations 0000 to 00FF are called the trap vector table. When I issue an instruction to trap 21, 21 refers to the spot in memory, the actual spot in the trap vector table that holds the first address of my service routine. So in this example, trap 21 was a service routine I wanted to invoke. At memory address 21 is the value 0306. 0306 is the memory address of the first instruction in that service routine. And I can also invoke service routines or the trap instruction from inside a trap routine. In this case, the process is the same, a little bit simpler, because I'm already in sort of a privileged mode. I'm not moving from user space to supervisor space. I'm already there. And then there are a number of instructions that are available to us. There are a number of trap routines that are available to us, which are discussed in the text that, like I said, I'd encourage you all to get familiar with. All right, that's all I got. See you next time.